Ever wonder how physics actually describes something as simple as a journey from one point to another? You know, just getting from A to B? It seems pretty basic, but underneath that simple question is this beautiful and incredibly precise language that can actually predict the future.
So here's our game plan. To really get a grip on motion, we're going to build this up from the ground floor. We'll start with the basic words physicists use, the language of motion. Then we'll look at the rules that connect everything. And finally, we'll see how a single picture, a single graph, can tell the entire story of a journey.
All right, so to even start talking about motion, we've got to learn the language, right? And it all starts with three fundamental concepts that build on each other just perfectly.
So first up is position. It's the most basic question you can ask. Where is this thing? But in physics, where always needs a reference point, an origin, a starting line. So position just tells us an object's location relative to that starting point. Simple enough.
Okay, now things get a little more interesting. If position tells us where an object is, velocity tells us how quickly that position is changing. So we're not just talking about a location anymore, we're talking about speed and direction.
And this is the real secret sauce. Is the object speeding up? Is it slowing down? Is it changing direction? That's the story that acceleration tells us. It's literally the change of the change.
Okay, but let's pause for a second, because we need to get a little more specific here. There is a huge difference between your speed over a whole road trip and your speed at one specific moment, and getting that distinction right is absolutely key to understanding motion.
And this is a perfect way to think about it. Average is the big picture summary of your journey. You drove 120 miles in 2 hours, so your average speed was 60 miles per hour. Instantaneous, on the other hand, that's the close-up. It's what's happening this very second. It's the exact number you see on your car's speedometer right now.
So when we talk about average velocity, we're really just talking about your total change in position, your displacement, divided by the total time it took. It kind of smooths everything out, all the times you sped up on the highway and all the times you got stuck in traffic.
Now this formula, v equals dx over dt, it might look a little scary, but trust me, it's not. It's really just the core idea of what instantaneous means. All it's saying is the change in position, that's the dx, over a tiny, almost zero sliver of time, the dt. It's just a fancy mathematical way of capturing that exact reading on your speedometer at this very second.
And you know what? This exact same logic applies to acceleration too. You can have an average acceleration over, say, a few seconds, or you can have that instant jolt, that push you feel in your seat the moment the light turns green and you hit the gas. Big picture versus right now.
All right, now that we've got the lingo down, let's look at the actual rules of the road for a special, but super common type of motion. Constant acceleration. A classic example? Just think about an object falling under gravity.
Okay, these 4 equations, think of them as the physicist's crystal ball. Seriously, this is the toolkit for predicting the future. If you know where an object starts and how it's accelerating, you can use these formulas to find its exact position and velocity at any point in the future. You don't even have to watch it happen.
So, how do we use this stuff? Well, let's take a puzzle like this one. You've got 2 different stones dropped from different heights at different times. They land at the same moment. It seems kind of impossible to solve without actually seeing it. But if we just apply those rules, those equations from our toolkit, we can figure out the exact height of that tower, 31.25 meters. We didn't measure it. We predicted a physical property of the world just by using math. That right there, that's the power of physics. Okay, equations are powerful for sure. But what if you want to see the entire story of a journey all at once? Well, for that, we turn to maybe the most powerful storytelling tool in all of physics, graphs. First up, we have the position versus time graph. Just imagine it's a storybook of the object's location over time. And here's the really cool part. The shape of the line tells a story. If the line is really steep, the object's moving fast. If it's flat, well, the object's just standing still. The slope of that line is its velocity. Now this graph, the velocity time graph, this one is absolutely packed with information. It's telling us 2 completely different stories at the same time. First, the steepness of the line, its slope. That tells you the object's acceleration. But second, and this is amazing, the area underneath that line actually tells you how far the object has traveled, its total displacement.
And this is the perfect way to see the difference between distance and displacement. Think about it. If you walk forward 10 steps and then backward 10 steps, you've walked a distance of 20 steps. But your displacement, your change from your starting position, is 0.
The area under the graph shows us both. You add up all the areas for distance, but you subtract the negative parts when you're calculating displacement.
Okay, theory's great. Let's put this to the test. Let's try to read the story that's hidden inside a real graph and see what it can tell us. All right, take a look at this graph. It's showing us an object's acceleration over an 8-second trip. The question's pretty simple. At what point in time does this object get back to the exact same velocity it had at the very beginning, at time 0?
So where's the answer? Well, it's literally hidden in the area under the line. For the first 4 seconds, that positive area shows us all the velocity the object gains. Then, from 4 to 8 seconds, that negative area shows the exact same amount of velocity being lost. The gain and the loss perfectly cancel each other out. So at t equals 8 seconds, the total change in velocity is 0. It's back to where it started.
So what this really all comes down to is that these graphs, they're not just lines on a page. They are complete stories of a journey. The slope is like the plot. It's what's happening. And the area is the outcome. The entire story is right there for you to read if you just know the language.
So we've seen how we can translate something as real as physical motion into this clear, predictable language of physics and graphs. And it kind of leaves you with this one big question, right? If a simple graph can tell us the entire past, present, and future of a journey, what other powerful stories are just waiting to be told, hiding in plain sight in the data we see every single day?